Okay, well, I'll try to keep my lecture brief since it's so late. I first want to go back and just make a few more comments about manipulation of chiral domain walls, and then I want to turn to the interesting subject of scamions and anti-scamions. But first, somebody asked a question about sputtering systems. So I thought, just for relaxation, I'd show you what one of our sputtering systems, what we're building, looks like. And this is the system we're currently building in my institute, and it's basically about 5 meters long and about 3.6 meters tall and weighs several tons and costs several million euros. It's still not entirely complete, and it has about 40 different sources. And the top chamber, you cannot see, this is a very long chamber in which we can move a substrate, rotating at temperatures of up to 1,000 degrees centigrade, 2.6 meters, using an internal robot. And it's controlled by software that we've written using Beckhoff. And here you can see in a cartoon, these are substrate holders that hold substrates only 1 inch in diameter, up to 1 inch in diameter. And then this is how we of course have to build the system, and so we have to model it and then build all the parts. It's quite a long process. It's taken, as I said, about 2 years. But now, and then we have this control system. You can see here we are. It's automatically controlling the system and will robotically be inserting a series of substrates. And here you can see we're actually depositing a film. So here on the right-hand side, you see a robot arm comes in, and it's going to take this. This is the real system. It picks up a substrate holder, which is made from a very special Haynes metal alloy that can sustain temperatures of 1,000 centigrade in pure oxygen. Then it moves to another part of the system you see on the left-hand side, where it's going to put the substrate into the substrate holder, where it can be heated and rotated. So unfortunately, this is a little bit slow. You see, it's left it there, and now it retracts, and then you'll see in a moment or two more happening. It takes a little bit of time. Sorry. This is the control system. So it's automatically automated, so that now you can see substrate holders. This is now a quartz crystal monitor is detecting the flux of atoms from the source. You can see some other things happening here, and then eventually you'll see the substrate holder move over on the left-hand side. This is basically opening, injecting some gas into the system, controlling the pressure. That's a quartz crystal that's monitoring the rate. You can see a flash of the magnetrons because it takes a few seconds to deposit a single layer. Now there's the real substrate holder. It's rotated, heated, goes down into the deposition. That's the plasma lighting. You can't see it actually. And then the film has been deposited. It takes 2 seconds per angstrom approximately. And then now it's moved over here, and we're going to do some other things. There we are. That's basically how it works. And it's a rather complicated system, but it has a lot of capability for rapidly exploring materials. This is the idea. All of these different chambers in the system with 45 different materials can be exchanged without opening the system to air, the main system. So we can continue to evolve and make films. This is very unusual for any of these systems. It's the only one of its type in the world. Anyway, and now it's, you can see finally, eventually you'll see the magnetron light. This is a rather special part of the system. We actually have 12 magnetrons, which are these where we contain a material and which we use magnetic fields to locally create a plasma. And we have 12 magnetrons on like spokes on a wheel. So now you can see now these are one of the 12 magnetrons, and then it will rotate to the deposition position actually, and then you'll see the plasma light, and this will be a target of magnesium oxide, which is a very important tunneling junction barrier material. Now this is the source. Then we introduce some gas, we apply some voltages, and then we excite the plasma, which you'll see in a few seconds. Hopefully. But you will, in a few seconds. It takes, then we just, you see that's the plasma, and now that actually is the target. This is RF deposition of magnesium oxide. It's a very nice material. Okay, there we are. So that was a brief interlude. And now back to Racetrack. So what I did this morning, I tried to explain that to manipulate chiral domain walls, we use a combination of several different spin-orbit related phenomena, one of which is the spin Hall effect. And that's simply, we can convert charge current to a perpendicular spin current with a spin polarization perpendicular to those two directions. And over the last few years, it's been determined by ourselves and one or two other groups that even simple metals like platinum, tantalum, tungsten show very, very large conversion efficiencies, much larger than were anticipated just a few years ago. And then, as I mentioned, there is some very speculative work on topological insulators which appear to show very large conversion efficiencies which exceed 1. That means you can have, in the case of the work from UCLA, they suggest you could have 100 spin polarized electrons created for 1 electron in the current. This would be fantastic technologically, but nobody else has confirmed these results yet. Now, I just want to give you a very cartoon impression of how these effects work to move a domain wall. So now we're looking on the top of this racetrack. So remember, we make the racetrack by depositing on a flat substrate atomically thin layers of cobalt, nickel cobalt, a little bit of platinum underneath, and so on. So it's really just atomically engineered. Now you're looking on the top of the racetrack. This is the cartoon. Blue regions are pointing towards you, magnetization pointing towards you, red regions pointing away from you, and the region in between is the domain wall, which in reality is just 6 nanometers in width. And now what we do is, because of this Dirizinski-Mirya exchange that I mentioned earlier from the interface with the underlying platinum, this generates these exchange fields, which are vector and chiral. And so on the left-hand domain wall, where it rotates from an up, the blue direction, to the red direction, the exchange field points to your left. The next domain wall over, where it goes from a down to an up spin direction, the exchange field points to your right. And that sets the chirality of the nail domain wall, which is very important. Now we introduce a current through this platinum layer underneath. That generates this spin current. The spins that are accumulating will then diffuse into this magnetic layer, and as I mentioned earlier, this will provide a torque. And this causes the magnetization to rotate towards that direction of spin angular momentum. And now the magnetization, you can see, no longer lies along the exchange field, because there's an angle, there's a torque. And that is the torque that actually then drives the domain walls. And the torques are such that on the left-hand side, then the blue region will grow and move to the right. And on the right-hand side, the red region will be moving to the right. And this is why the two domain walls move in the same direction. If they had different chiralities, this would not be the case. If we change the chirality, let's say the Dirizinski-Mirya exchange on the right-hand one, then the domain walls would move in the opposite direction. So the chirality of these nail walls is essential and is what determines the motion of these walls at these very high velocities. Now they move at several hundred meters per second. That's the basic idea. And as I mentioned earlier, I'm not going to discuss this in any detail. In this case, the torque is really determined by the strength of this Dirizinski-Mirya exchange field. The bigger it is, the bigger is the torque. It's as simple as that. And in the case of these synthetic antiferromagnetic racetracks, which again, we just take one domain, one racetrack, we put another one on top, which is identical, but using this trick of a very thin layer of ruthenium in between, whatever is the magnetization profile in the lower racetrack is exactly mirror imaged in the upper racetrack. Every magnetization in the lower racetrack is imaged in the one above in the opposite direction. And this exchange field through ruthenium, which is antiferromagnetic, is extremely strong, much higher than the Dirizinski-Mirya exchange. And this exchange field itself gives to a giant torque that then will move these domain walls much more efficiently. And then what we see is that if we completely balance these moments, we see this giant velocities, which are a record. Nobody's seen these velocities before, exceeding a kilometer per second. And this is what makes this very, very interesting. So what I've tried to do then is go from a simple racetrack, this perpendicularly magnetized copper, nickel, cobalt. You see all these domain walls moving at the top and underneath. And down below, you see this synthetic anti-ferromagnetic racetrack. And really, this is a really complex interplay of 4 spin-orbit-derived phenomena: the perpendicular magnetic anisotropy, proximity-induced magnetization in platinum, the Dirizinski-Mirya stabilized chiral domain walls, and the spin currents generated from spin Hall effect, all working together in these atomically engineered layers. And this is quite interesting, very difficult to have unraveled. And so just another aside, we can actually directly measure the strength of this Dzyaloshinski-Murray exchange by compensating that exchange field with a longitudinal field along the racetrack shown here. And without going into any detail, if you just look at the top left, you can see the velocity of the domain wall as a function of this longitudinal field. You can see for different current densities. So it basically varies linearly with this longitudinal field. But there's a magical field, perhaps you can see over here, irrespective of the current density, where the domain walls simply stop moving. And it's asymmetric, it's a negative field. And it's a field that exactly compensates the Dzyaloshinski-Murray exchange field. When they compensate, we no longer have nail walls. We have block walls, and this spin orbit torques I've discussed cannot move the block wall, so they stop moving. So this is how we discovered that we had this very interesting Dzyaloshinski-Murray exchange field. And you can see on the top, on the top left, this is for domain walls which have going from a down to an up direction, and you can see the next domain wall going from up to down has, you need the opposite sign of the longitudinal field to stop the walls, because the Dzyaloshinski-Murray exchange field is exactly the same magnitude, but of the opposite sign. And this is how we know we have these chiral domain walls. So this is a very, very simple but very beautiful illustration of this Dzyaloshinski-Murray exchange and how it works. And you see this for different underlayers, palladium, platinum, iridium. The strength of the exchange varies. So it's most dramatic in the case of platinum. For palladium and iridium, these magical fields where the domain will stop moving are much smaller. And interestingly, with gold, which is a very heavy metal, there is no spin-orbit coupling effects, and in this case you can see this longitudinal field has no effect at all on the velocity of the domain wall, because here the domain walls are moving, as I mentioned earlier, in the opposite direction through an entirely different mechanism, which is due to the polarization of the current passing through the cobalt, nickel-cobalt layers themselves through spin-dependent scattering. It's totally, totally different. And so you end up with this very interesting phase diagram that as we increase this, longitudinal field along the wire, you essentially change even the nature of the nail wall. You can change its chirality, and then the velocity of this wall will change, go through zero at this magical field, but then go in the opposite direction for bigger fields, because it looks like a different type of Dzyaloshinski-Murray exchange. This is how we know it all working. And we can actually model all of this using a concept, a very simple model in which we assume the domain wall profile does not change as it moves, which is not always the case. And then this is a so-called one-dimensional model that was developed for field-driven motion of domain walls and magnetic bubbles in the 1980s. We've developed it now for introducing these spin-orbit torques and spin-transfer torques. And so we can take a case, let's say in zero longitudinal field, and then what you'll see here is that this shows you a top view of the domain wall, and this is a side view of the up-down and then the down-up domain walls. So the two successive domain walls. And then if you look, this is how we model on the nanosecond pulse. This is 1 nanosecond. You can see that this is what happens. The two domain walls move at exactly the same velocity. And if you look very carefully, you can see at the very beginning, the wall is rotating. The magnetization rotates to this sideways direction due to the spin-orbit torques. Now what happens is we can change this field to this crossing field where the one domain wall stops moving, and indeed that's what we find. One domain wall now with current doesn't move, and the other one will move faster. And similarly, if we change the opposite field, then the opposite domain wall is stopped, and the other one moves much faster. So we understand now this, we think, very, very well, the mechanism behind the motion of these domain walls. But as you can see, it's not so straightforward. And so just to summarize, you have this very interesting interfacial driven mechanisms, and we can control these two chiral effects The Dirichlet-Maria interaction is chiral. The spin Hall effect is chiral. And they have opposite effects at the top and bottom interfaces. We can design these interfaces so that these effects are additive or subtractive, and so we have a lot of ways in which we can tune the velocity and the direction of these domain walls in this way, because now we think we have a very, very good understanding of this mechanism. I wanted to just briefly mention, which I think I will skip, that it turns out that very interesting, we discovered just recently, is that if we have a curved racetrack, so now you can see here, this is a lithographically defined curved racetrack, and this shows you what happens if we have, here you can see two domain walls. This is a domain pointing up, and here it's pointing down, so we have a domain wall here and another one here. Now we apply a series of current pulses, and this is what it looks like afterwards. You can see this front domain wall has moved faster than the one behind it. So now the two domain walls in a curved wire actually move at different speeds. And surprisingly, this is something that we and nobody else appreciated for quite a long time. We just realized this quite recently. Depending upon the curvature, then the walls move at different speeds, and this shows you the velocity experimentally that we measured as a function of current density for different curvatures. And it also depends on the width. The wider the width, the bigger is the difference in the velocity of these successive domain walls. And it depends simply on the curvature. That determines this ratio of velocities in this way. And again, without going through details, the reason for this is you can understand quite easily. Here we have a curved wire, racetrack, and you can imagine if we want this is magnetization pointing up, and this blue is pointing down, and now here what happens is the domain wall in the absence of current will be along the radius, because that's the shortest. But as soon as you apply current, what happens is in order that we have a domain wall that moves along this wire as one unit, then it turns out, as you can imagine, on the outside of this curved wire, basically it's longer. The circumference is 2 pi times the radius. So you have to rotate or move more magnetization on the outer part of this racetrack than on the inner part. And the amount you have to rotate goes linearly with the radius. And so what does that mean? That means you need more torque on the outside than the inside. And the only way to sustain the constant motion of a domain wall is that the domain wall itself converts itself from a straight domain wall into a wall with a very particular shape, such that the torque on the different parts of the wall increases linearly across the radius. And that's exactly what happens, and we can model this precisely, and it turns out there's two interesting time scales within the wall itself. Because of the spin Hall effect, the magnetization, as I showed you earlier, will be rotated towards the spin current. But at the same time, to establish this particular shape of the domain wall, then we need to rotate all of this. This red region here was originally blue, and this blue region here was originally red. We have to switch all that magnetization, and that turns out to take a very long time. So within the wall itself, the wall moments rotate in response to the spin Hall torques very rapidly, but this takes much longer, and we have two different timescales, and the timescales for this turning the wall into a straight to this complex shape that determines the constant motion of the domain wall takes tens of nanoseconds, whereas within the wall itself, it will evolve in a few hundred picoseconds. This is what happens, and then we can model this, and now we understand what's going on. And as a very interesting conclusion, it would be that, of course, from a technological point of view, this would not be good. If we had racetracks with a little bit of curvature, it would be a problem. But it turns out, once again, that this synthetic antiferromagnetic racetrack, where we eliminate magnetization, where the domain walls already go super fast, it turns out this is insensitive to the curvature because the upper and lower racetracks respond exactly oppositely. And so then we have straight domain walls, and they move. As you can see in this experiment, here we have two domain walls here, and after we've moved them all the way around, they have the same spacing. And so this is a very, I think, beautiful demonstration of technologically and physics. This is what we need. So I want to move to these skirmions, but how about Racetrack? I mentioned at the beginning, we want to eventually, the goal, motivation for Racetrack, the reason why I invented it originally was to build a super dense racetrack with vertical wires with 100 domain walls. We believe that's possible, but it's going to take a lot of engineering. Another very interesting possibility is we could build what I call one domain wall racetrack, where we have a very short wire, 100 nanometers long. We move a domain wall backwards and forwards with current. It moves at a kilometer per second. We detect it with an integrated tunneling junction. And this type of device turns out to be as fast as the fastest memory that you could buy today, but it uses much less power, is non-volatile, and it has a density which is several times greater than the densest static random access memory today. And so we think this is a very exciting near-term possible use of racetrack memory, and we have a lot of interest now, for example, from Samsung, who wants to work with us to see whether we could do this. Now, this was racetrack memory, which I think has gone over the 10 years since I first proposed it. There's a lot of interesting science that was unexpected through all of these spin-orbit related phenomenon. And I want to briefly then move to this question of skirmions and antiskirmions. So I think many of you are familiar with this. About 10 years ago, Christian Pfleidra discovered that in manganese silicon, a particular material, he found evidence for these Block skirmions. What are they? If you have a material which is magnetized in a perpendicular direction, it turns out there's a ground state in which the system breaks up into small magnetic bubbles, which is a skirmion, where the magnetization is reversed in the middle of this bubble, but the wall is topological and is chiral, unlike a conventional magnetic bubble. And on the left side, the wall is a Block wall, which simply means, as I mentioned earlier, the magnetization rotates from the outside to the inside, and it rotates in a plane which is parallel to the wall. You can also, in some other systems, since in the last 10 years, a number of systems have been found that show these skirmions. And in other systems, it's found that they're nail-like. So just like the chiral domain walls we've been discussing, which are nail-like, you can have a wall around this object, which is nail-like, in which the magnetization then rotates up to down, but in a plane which is perpendicular to the boundary of this nano-object. So this then, now it's well established that one sees Block skirmions and nail skirmions in distinct materials. Maybe there's 10 materials where it's been seen now. Typically, magnetic field is required to stabilize them. Typically, you see them at low temperatures, so it's not so exciting. Now, how do we see these objects? And the simple way to see them is using something called Lorentz transmission electron microscopy. Very, very simple cartoon on the right. Basically, what we do is we take a beam of energetic electrons, a nanometer wide, in a transmission electron microscope. And this beam of electrons is passed through a very thin lamella formed from this material. So we have a lamella of this magnetic material. It's sufficiently thin that this 300,000 volt beam of electrons can pass completely through it. And as they pass through it, they feel Lorentz forces from any magnetic moment directing in the plane of this lamella. And we can calculate what we expect to see in this microscope. And this is what we've done. This is a student of mine, Jianping Ma, calculated this. So first he simulated using micromagnetic simulations a nail skirmion and a Block skirmion. And then he calculated what we expect to see in this Lorentz imaging mode of this transmission electron microscope. And very trivially, it looks like this. If we take a Block skirmion, then as the electrons pass through, they will feel a force that forces them to move to the outside or to the inside. And so you end up then with basically a blob. You see this white blob. That's what you see. In the middle, and a black circle around it. On the other hand, in a nail skirmion, because of the different form of this chiral wall, the electron beam now is moved to around the circumference. So basically, the electron beam is moved around the circumference, so nothing happens, and you see nothing in the case of a nail skirmion. So I want to talk not about nail or Blockscomience. I want to talk about Antiscamions. So an Antiscamion is shown here. This is, as I said, a simulation. And what happens in the Antiscamion is that the wall type changes as we move around the Antiscamion. And it changes from a block type to a nail type, back to a block, nail, block. So around the circumference, it alternates between a block wall and a nail wall. And what does that mean? And then again, if you go through the simulation and calculate the forces on the electron beam, then as the beam is transmitted, now you should end up with something that looks like this, a little bit like a clover leaf, but two of the clover leaves have high electron intensity and two have reduced electron intensity. Now all of these images are calculated for the beam being exactly perpendicular to the lamella. If it's not perpendicular, then the images will be distorted, and that's typically what one sees. So where are we going to look for antiscamions? So it turns out it was theoretically predicted that in certain materials which have a certain symmetry, a D2D symmetry, you should see antiscamions and not scamions. And that is why we looked at this Heusler family of compounds that Claudia discussed in her talk. And these are materials made in her group in Dresden. And these are a series of Heuslers in which they have heavy metals, rhodium, iridium, and platinum. And then it was, because of strong spin-orbit coupling, these systems, this gives rise to this Diriginsky-Maria exchange, and you end up with non-collinear spin structures in these systems. Now, there was some evidence for that from the magnetization, which varies as a function of temperature, and at low temperatures you see some kind of phase transition, which Jürgen Kubler, who's a very, very good and fantastic theorist who calculates band structures and structures, proposed that there was a structure in which the magnetic moments in this Heusler become non-collinear at low temperatures. So a Heusler material, as Claudia discussed, typically has these 4 interpenetrating lattices, FCC lattices, and these are a special subset of these materials which are tetragonally distorted. And then you have the moments are pointing along the tetragonal axis, and there are 2 sublattices of these manganese atoms. One sublattice points up, let's say, and another points down. So this is a collinear antiferromagnetic or ferromagnetic structure. Low temperatures thought to become non-collinear, something showing like this, where the one sublattice of manganese has its moments rotated by a significant angle, 30 or 40 degrees. This is what Jürgen Kubler calculated. And there was some evidence we found some evidence for so-called topological Hall effect, which is thought to be observed in these scamionic systems or anti-scamionic systems. I'm not going to talk about that. Let me try to show you some data. This is all very relatively new. We just did this in the last year and a half. And so here is a conventional bright field transmission electron micrograph where you can see all the atoms, and we can see that we have a beautiful lattice. And then what you can see in the Lorentz mode is, can you see here, you can see these black and white stripes. And what these black and white stripes correspond to is actually a helical phase, not a scamionic phase, a helical phase where the magnetization is rotating from one direction to another direction, and so we see the component of magnetization in plane changes from black to white, and that's what we're detecting in this Lorentz mode. And then over here, you may be able to see these are an arrangement of antiscamions. So let me show you in more detail. So this is one of these objects, and so can you see it looks pretty much like our simulation? Would you not agree? So this is the first ever observed antiscamion. So we published this last year in Nature. And these antiscamions, just like scamions, they form an array. And they form an hexagonal array of these antiscamions. They have a certain size and a certain separation. We can mimic all that in our micromagnetic simulations. And just like the scamionic phase, as you change the temperature or you change the field, you can change the stability of this phase. That's what we can see. So this is just to show you as we change the temperature of field, you can change the spacing and size of these antiscamions. And what we find then is this is the temperature in our system, we can only go down to 100 degrees Kelvin, up to 400 degrees Kelvin, and for perpendicular fields varying from up to 0.6 Tesla, we basically see all of this region is where we see these antiskermions, and the green is where we see the helical phase. So the helical phase evolves into the antiskermions, and at high enough temperatures or high enough perpendicular field, we of course stabilize the ferromagnetic phase. So there are three phases: the helical phase, antiskermion phase, and then there is the ferromagnetic phase. So I want to discuss one very interesting aspect that we have very recently discovered. And I want to do this by first reminding you of what happens with skermions, in particular in this iron germanium system. This was the system that Yoshi Takura and his group found a few years ago after the manganese silicon. It's a B20, it's a chiral phase. And what they found was, you can see there skermions, they're just these blobs. And they found then they could look at they changed the thickness of this lamella through which we're imaging with the Lorentz TEM. And they found that this is a very thin lamella, 15 nanometers thick. And as they increased it to 75 nanometers, you see this red region is where they see skermions. This again is perpendicular field and temperature. And they found that basically it almost vanishes as you increase the thickness of this lamella up to 75 nanometers. So we think, and they basically couldn't really understand why this happens. And this was some time ago. We think we understand why this does happen. So I want to contrast this with our own work on antiskermions. So what do? Using something called a focused ion milling capability, which is a beam of gallium ions we could use to sculpt lamella from a single crystal. We make a lamella which basically varies in thickness along a wedge. Shown here. This is a scanning electron micrograph of one of these wedges we've created. This is 500 nanometers long. And then on the right-hand side, we use something called electron energy loss spectroscopy in the microscope to determine its thickness. So I don't want to discuss this, but we precisely can determine the thickness of these lamella. And now what we look at is, here is this wedge. And here we have three different regions along the wedge of different thicknesses, A, B, C. And here you can see this is the initial image, and we increase the magnetic field. And you can see as we do that, we see these skermions, or we see these helical phase. So it's going from high field here to low field here. So this is the ferromagnetic phase. And then you see in this region A, which is the thinnest region, you can see here's the antiskermions, here's the helical phase. And you can clearly see, I think, that depending upon the thickness, we can see antiskermions or not. So the phase diagram has some dependence on thickness, but it turns out it's relatively weak. So if we look at this on the right-hand side, we're plotting the number density of the antiskermions. And we basically, as a function of increasing thickness, this is 160 nanometers, this is 247, and you can see, irrespective of the thickness, we see large regions in which we can see these antiskermions. This contrast to the skermionic phase that disappears. And there's also another very, very interesting point we discovered, which is if we look at the helical phase in these different thickness regions, we see that the period of this helix varies considerably with thickness. It's varying from 100 to 250 nanometers as the thickness evolves from 40 nanometers to 180 nanometers. Difficult to explain that using conventional models for skermions or this helical phase. But it actually turns out to be even more dramatic. So in this Lorentz transmission electron microscopy, we're limited in thickness of the lamella to thicknesses through which we can transmit this electron beam, which is about 500 nanometers. But we can instead use another technique I'm sure you're all familiar with, which is magnetic force microscopy, and we can do that as a function of temperature and magnetic field. And here we've made a wedge, which is 4 microns long and 4 microns wide. And this is the wedge which we've created by this sculpting technique using beams of gallium ions. And then what we find as we move along the wedge, this is the thickness region, 60 to 50 nanometers up to a micron, we find that the period increases, continues to increase, of this helical wavelength, and it's increasing up to 500 nanometers here. So what we find, quite remarkably, is that the period of this helix increases almost linearly. Up, you can see 1.6 microns is this thickness from magnetic force microscopy. So the magnetic force microscope is directly imaging the magnetization, which again is rotating from in plane in this way. So this is amazing. This has never been seen before, and we believe we know why this is. It turns out that this is, as I was emphasizing in Racetrack, it's actually due to dipole energies. And the dipole energy is what is causing the wavelength to increase in this way. And this is totally, nobody's seen this before, and nobody has actually appreciated the significance of these magnetostatic effects on both the helical phase and the antiscamion phase. It would also be true for scamions, but for a different reason they cannot see it. So this is quite remarkable. We're quite surprised. We have a lot more data I'm not going to discuss, but we can actually, again, carry out micromagnetic simulations, and then we could use these simulations to look at the stability of this antiscamion phase. So just to show you some representative simulations, we're increasing the magnetic field, and you can see we go from a combination of a helical and antiscamion phase to antiscamion to the ferromagnetic phase. We can see all that. And to cut it very brief, what we see is, and I'm sorry for the very poor quality here, this is some very recent calculations. This is the B20 structure that supports the scamions. This is increasing thickness from 1 to 18. This is numbers of layers in our simulation, which in this case is 14 nanometers. So it's up to 18 times 40 nanometers. And this is the magnetic field, which goes from 0 to 3,000 Oersteds. Now, I can't show you it in detail, but what we find is this is the scamion region. And you can see, indeed, as a function of increasing thickness, it's eliminated, just like the experiments of Takura. However, for this D2D symmetry structure, which supports antiscamions, we find that this antiscamion phase is sustained, irrespective of the thickness, just as we see in our experiments. And the reason for this is very simple to understand. Due to the symmetry of the different crystal structures, B20 is cubic. And so it means in X, Y, and Z, you have a Dzerzhinsky-Meyer vector component of this exchange. And that means you basically twist the structure in all directions. And so it's not possible to sustain the scamion in the perpendicular direction. However, in the D2D structure, it's such that along this vertical direction, there is no twisting of the structure because there's no component of this Dzerzhinsky-Meyer exchange vector. So we think it's as simple as this. It's the symmetry of the components of this DMI vector that determine these phase diagrams. And this is something that hasn't really been appreciated. And we've actually calculated now what we expect to see for all sorts of different symmetries, and some of them are very, very interesting. So I'm not going to say more about it. We can actually understand completely now the thickness dependence of the helical wavelength. And we also see at the same time the skyrmion size evolving just with the helical wavelength. So the skyrmions go from 100 nanometers in these thin lamella to more than a micron in size for thick lamella. And we can image them using Kerr microscopy, and we can image them using magnetic force microscopy. It's extremely interesting. And we have a detailed prediction of how the helical period and the size of these antiscamions will vary with the thickness of the lamella, which it turns out to be even more interesting than I have presented. So just final then, as a final aside. Skyrmions, you might say, why are they interesting? And I think they're interesting because it's a fundamental new phase of matter that we've discovered, these antiscamions. And of course, it has been proposed by a number of people that they could be useful for racetracks. And this is a very nice cartoon from Axel Hoffman at Argonne National Labs, where he published a paper a couple of years ago showing that he could use not really skyrmions, these are actually really magnetic bubbles, but he could see them moving in sort of this racetrack that they created in this way. But of course, I like to say, well, they're actually moving incredibly slowly. They're moving at speeds of this, you see, 0.000001 meters per second. Current densities of 10 to the 5 amps per square centimeter. So in the skyrmionic community, people think it's really interesting technologically because they can be moved at extremely low velocities. Well, actually, we can do the same thing with chiral domain walls. And it turns out technologically it's not very interesting. If they move, you don't want them to move until you exceed some threshold current, in my mind. Nevertheless, a lot of opportunity to create new types of non-collinear spin textures that have very interesting, distinct properties depending upon the different spin textures, including spin Hall effects that we discussed, topological Hall effects where the electron trajectories are twisted inside these skyrmions or antiskyrmions. And again, it turns out antiskyrmions are really interesting. It turns out the twisting of the electron trajectory depends on the crystal orientation through which the electrons are passed. And because of this nail and block type walls around the antiskyrmion, there are some crystalline directions in which the electron trajectory is not affected and other directions in which they'll be moved to the left and to the right. This is super interesting. Skyrmions, the trajectory is always twisted to the left or to the right, giving rise to this topological Hall effect. So then I guess come back then to a summary. Racetrack memory, we come back then, we maybe potentially have two varieties. One variety in which we could have a single domain wall or maybe even an antiskyrmion moving backwards and forwards at these super high velocities, enabling us to build some kind of super high performance memory to replace SRAM. On the other hand, if we can deposit the appropriate materials on vertical walls, we could build this vertical form of the racetrack, which would have a density exceeding any memory today by about 100 times, and about the same capacity as today's magnetic disk drives, but in a much smaller form factor. And it has all sorts of interesting aspects, including its reconfigurability. And so this is what is needed is, as we discussed, somebody asked a question, turns out to take full advantage of this racetrack, you need to change the circuit and computer architectures. And that's, a lot of people are thinking about that today. So I just want to summarize then, I think spin orbitronic technologies are super interesting. They've evolved over just the last few years. And they enable manipulation of magnetization using physical phenomena that wasn't anticipated until quite recently, promising very, very interesting potential new technologies. And at the same time, I think these new forms of spin textures, I've just discussed one, antiskyrmions, are very interesting. They have very distinct properties which could potentially be useful, maybe not for racetrack, but maybe for neuromorphic computing. And so I'd like to thank the people involved in this work, and these are some of our more recent papers that you might want to view. So I'm happy to take any questions. Thank you very much. No, it doesn't matter. Yeah.
Yeah. Know where to say it's 0 or 1 if it's you have a fixed width, I guess.
So I think it's a very interesting point how we would do this, but basically the racetrack is the absence or presence of these domain walls. So there would be different spacings where you have no domain wall and where you have domain walls. Would be one way of storing data.
Yeah, but you need to control the distance between domain walls.
Well, we would control that by basically how we would inject the domain walls into the racetrack. But I think your question is a very good one. What we've basically demonstrated is we know we could now, for the first time, manipulate these walls at super efficient, so it makes it interesting. Now we have to really worry about exactly the question that you're asking, which is a very interesting one. But I think here, what's actually very exciting is that there's a lot of potential for invention and new concepts, which makes it, I think, very interesting all by itself. Skyrmions, that's a very interesting question. We think it's not possible because the symmetry of the local crystal symmetry determines whether you have a skyrmion or an antiskyrmion. An antiskyrmion is because you have different components of this Dirizinski-Mirror exchange in different crystallographic directions, stabilizing nail or block walls. So it's not, we don't think it's possible to have skyrmions and antiskyrmions in the same material. Yeah. Well, then it would be the presence or absence of a skyrmion or antiskyrmion. So he was suggesting this question. Then you need to know, just as he said, you need timing to know when to look for a skyrmion, and the absence would be a 0, let's say, and the presence could be a 1. It may not be the best way to do it. That is one possibility. Actually, quite frankly, we thought about this before, a long time ago, that you could actually take two chiral domain walls, and that could be the element itself. Instead of using one, you could store two, which is pretty much like a skyrmion. It has some advantages. What is the question? Yeah.
Wires you took in the first talk. Is it the same speed or no?
Well, you see the antiskermion.
Domain,
Yeah.
what if you inject antiskermion?
Oh yeah. Okay. Yeah. If we took a material which would sustain antiskermions, then we could inject an antiskermion. Quite frankly, we don't know how fast they move because we haven't moved any yet. And currently, I believe that it's not possible to move the skyrmions or antiskermions simply by passing current, because they typically, all of them contain heavy elements, and this gives rise to loss of spin coherence. However, by injecting currents using spin Hall effect from neighboring layers, which is currently what we're trying to do, we believe we've calculated that they should move very efficiently. So that's something we're currently working on.
Those two things, they are kind of different branches, they're not connected, right?
Yeah, they're not connected. That's right, yeah.